2 days left of this week. We're left at particle in the box, and we'll move to a new problem, a new model for a system that will be even more chemically relevant. I wanted to use today to convince you that the particle in the box is a useful model for chemistry, the chemistry of electrons in particular, how electrons move in molecules. And so I want to use a motivating example today, kind of a classic one. Recall that the motion in the box is one-dimensional, right? There's only one dimension of motion. So even though we call it a box, it's really the particles on a line. The height of the box is an energy property, but in fact, all the electron is doing is moving back and forth on a line, and the wave functions tell you where it is, the probability where it is a function of energy. Right? So as you go up to energy, the distribution becomes more complicated, but all we're looking at is an electron moving back and forth on a single line. Right? It's not really even a box. It's two dimensions in energy and position, but in terms of just position, it's just energy. Right? So it's a line. But it turns out that there are lines in chemistry where this structure works very well for us. And the motivating example I want to use today are molecules that look like lines. And the one that I want to consider is the molecule butadiene, which two different ways to draw it. There's two different isomers. Butadiene is a conjugated hydrocarbon. It's got two conjugated double bonds. I think this is called the cis. And it equilibrates with what's called the trans version of it. Trans. And it turns out actually the trans is the lower energy. So butadiene exists mostly in the trans form, and the cis form is higher in energy. So what I'm going to do today is think about our butadiene and the electrons inside the double bonds. The important thing to realize, this is back from, let's go back to orgo. I'm sorry that we have to do this. But if we look at the double bond system of this molecule, right, just the double bonds, right, we have these what are called pi orbitals at each carbon. Right, these are the pi orbitals. Right, and they're all in line, right? So there's in fact two sets of pi orbitals. There's one that's in the bond itself, and there's one that's perpendicular. Let's just worry about the perpendicular ones. Those are the ones that determine the fact that this molecule is planar. So the pi orbitals are effectively collinear. Okay, and so there are these orbitals can talk to each other. They have probability overlap. Right? We'll talk more about this when we get to molecules. Right, but these orbitals are all connected, and the electrons are delocalized through them, right? So the electrons, let me draw the color. There are, in butadiene, there are 4 pi electrons. And so these electrons sit in these orbitals and are allowed to move freely through the system. Right? They can exist anywhere in the molecule, and there's roughly equal probability. Well, it's not equal, but there's roughly some probability the electrons can exist anywhere along the chain of the molecule. So what do the wave functions of this look like at the energy levels of this pi system? Let me think about this for a second. Yeah. So you end up in these pi systems. You end up getting 4 wave functions. You have 4 atomic orbitals adding together. Right, these are these p orbitals. Right, these are the p orbitals on the carbons, if you will, to form 4 molecular wave functions. Right, we'll talk about this later in the class, how we construct these. Right, we'll be able to actually calculate this explicitly, but just bear with me for now. But when you add some number of orbitals together, some number of atomic wave functions to make molecular wave functions, you get the same number back. So we get there are 4 wave functions for the pi system. We'll call them psi 1, psi 2, psi 3, and psi 4. Right, this is for the pi electrons. And we can fill, just like atomic orbitals, we can fill them up with electrons. There are 4, so there's 2 sitting in the ground state and 2 sitting in the excited state. Just fill it in like you do a hydrogen atom or any atom. Right? You fill the orbitals up with your electrons, 2 by 2. And this is what you end up getting. And now the question is, so let's treat this system like electrons trapped on a line, which is just particle in a box. Okay, so we're going to treat this as 4 levels of a particle in a box, and there are electrons in different levels. And now the question I want to ask is, what is the energy difference? Call this H bar H omega, the energy difference between the two. That's energy by Planck's law. Right? For this electron to get excited to the next level. Right? How much energy do we need to put into an electron to excite it to the next level? Right? It's just the energy gap between the second and the third state. Well, we can calculate that very easily by using our laws. Right? We have particle in a box. We know the actual energies of every state. Right? They're proportional to the mass of the electron, the length of the box, right? And some number n, right? Where n here is 2 and 3. So the h bar omega, or h omega, the energy of this, which is the energy difference between the third state and the second state, right? How much energy you have between there, is going to be equal to the difference of the energies in the particle in a box. So that's going to be 3 squared h squared over 8 times the mass of the electron, L squared. I'll have to calculate L eventually. And the same thing for the second state. Okay. So we can do some factorization. Notice that they all have the same coefficient. We can factor that out. And it's equal to that times 3 squared minus 2 squared. That's 9 minus 4. So this is 5h squared over 8mel squared. Okay, so the particle in the box predicts that if we can calculate, we know the mass of the electron, I'll write it down in a second. If we know the length of the box, then the energy gap between, or the first excitation, if you will. If this is maybe you haven't learned these terms yet, but in organic chemistry they call these the highest occupied molecular orbital and the lowest unoccupied, the HOMO and the LUMO. The energy gap between the HOMO and the LUMO, if it were a line or a particle in a box, is 5 times this number. Okay, so let's calculate that. Right? We have everything we need to know. All we need to know is the bond lengths. So let's do that. So those are really easy to find. Butadiene is a well-studied molecule. You can use spectroscopy to determine it. And what you see is that the carbon-carbon double bonds, so this is the carbon-carbon double bonds, and this is the single, we'll call this single and doubles, which is the distance of the double bond, is 135 picometers. And then the single bond is a little longer, and that is equal to 154 picometers. Okay, so how do we calculate the length of our bond? Well, we're just going to assume it's a line, so we just add them up. Right, we have 1 single bond and 2 double bonds effectively in our system. So L is going to be 2 times the length of a double bond plus the length of a single bond. And that's 578 picometers, or 5.78 angstroms, however you want to look at it. Okay, so we know the length of our system. Just add them up from organic chemistry. And all we need now is the mass of the electron, which surprisingly I've never written down before, but I'll write it here. So the mass of the electron is roughly 9.109 times 10 to the minus 31 kilograms. Roughly. There's some more digits to that, of course, but that's good enough for our purposes. quite small, right? If you think about it, the hydrogen atom, which is a proton and neutron, is on the order of 10 to the minus 26. And so most of the mass of the hydrogen atom is neutron, right? Or the proton rather. Electron is like a 10,000th, no, yeah, 10,000th the size of a proton, right? So the electron is very small compared to the nucleus. So now we have everything we need to do to calculate it, right? Now it's just a plug and chug question. So now let's calculate H omega, our energy difference. And that's going to be 5 times the Planck's constant squared over 8 times the mass of the electron L squared. So we just have to plug things in. So this is going H, so we have a factor of 5 here. 5. Planck's constant is 6.626 times 10 to the minus 34 joule seconds. And then on the denominator, we have 8. Mass of the electron is over here, 9.109 times 10 to the minus 31 kilograms. And we're left with the length squared, which is 578 picometers. This is the same as 578 times 10 to the minus 12 meters. And picometer is 10 to the minus 12. Or if you're anal about it, should be 5.78 times 10 to the minus 10 meters. Right? Angstrom is 10 to the minus 10. So we can plug that in. 578 times 10 to the minus 12 meters squared. Okay. There's our predicted frequency. So we can calculate it. The units come out the joules. And you get 9.02 times 10 to the minus 19 joules. All right, it's a small number. Now, if we convert this to kilojoules per mole, which is what you're more used to, we're going to multiply this by 10 to the 23, and then which gives us in joules per mole. So that's going to be 10 to the 4 joules per mole, roughly 10 to the 5 joules per mole, divided by 1,000 to get kilojoules. That's 10 kilojoules per mole. Right? So this is kind of on the order of 10 kilojoules per mole, which is a pretty reasonable chemical number, right? Chemistry tends to happen on this scale, right? So this seems pretty reasonable, right? So we're already feeling like we're doing pretty good. The question is how good we are. And the important thing is to then apply Planck's law here to calculate the wavelength of light needed to supply this energy. We're always going to want to use light to interact with our system. Light's always going to be our energy source here. So we need to think about the wavelength of the light, this energy. And by Planck's law, which is E equals h nu, that's EC over lambda, HC over lambda, where lambda is your wavelength. So wavelength is equal to h times the speed of light divided by the energy difference. Okay? So we can just calculate that. We have everything here. We know the speed of light, we know Planck's constant, we know E. So Planck's constant is 6.626 times 10 minus 34 joule seconds. The speed of light is exactly 299,792,458 meters per second. Or 3 times 10 to the 8, however you prefer. And we know our energy, which is 9.02 times 10 to the minus 19 joules. Okay, so let's look at this number really quick. So we have minus 34, this is 10 to the 8, so this is minus 24 times, we have 18 here, 6 times 3 times, and then you have, let me think about this, 10 to the 8 times 10 to minus 34, that's minus 34 plus 8, just minus 26, plus a factor of 18, so that's minus 25, divided by 19, that should get us somewhere around minus 10 to the 10, 10 to the 9. And in fact, when you calculate, or sorry, 10 to the 7. Sorry, when you calculate this, you get 2.2 times 10 to the minus 7 meters. All right, so that's the wavelength of light you need. And this turns out to be 220 nanometers, right, because a nanometer is 10 to the minus 9. So this light is blue. This is blue light. This is blue or ultraviolet light. Okay, so what that means is that in order to excite an electron to give dyne, we need to shine blue light at it. Okay? And we predict that it's around 220. So we go into the lab and do the exact same calculation, or do this measurement, right? We put butadiene into a spectrophotometer. We tune our wavelength in the spectrophotometer until we find an absorption. And the absorption we find, I'll just write it here, experiment, is 217 nanometers. We're really, really close. Right? So by assuming a very simple rule that the molecule is the line, we get within less than 1% of the actual value. Something on the order. Well, it's not quite that. It's about percent. Yeah, it's about 1% error. In fact, when we get to the third rotation in the CHEM lab, for those who are in it this semester, we're going to do this exact experiment. We're going to do a series of conjugated systems. We're going to measure their absorptions in the visible. And these dyes, they're just dyes. They're dyes that absorb in the visible. Each dye has a slightly different longer chain, or line, if you will, right? The conjugated system gets longer, so L gets longer, and not surprisingly, the wavelength then is proportional to the length, or 1 over the length. And so as they get longer, the wavelength gets shorter, right? And so you'll be able to compare this prediction, this idea of using particle in a box to predict absorption of these dyes, visible dyes, using this system and compare the theory to the experiment. Right? You'll see you get very, very good agreement. Right? So in fact, in general, the absorption of conjugated systems like this are just particles in a box. You might think, well, this might fall apart very quickly. What if, for instance, our example molecule, what if our example molecule is benzene? Right? But now you don't have a chain, and now you don't have a line anymore, but you have a ring. Right? So this is a ring, not a line. And it turns out that you have to adjust your theory slightly. Particle in a ring. Right? Instead of particle in a box, you can come up with this, treat this as a circle. Right, so let's approximate this as a circle instead of a line. Do the same Schrodinger equation, solve for the wave functions, and calculate the energy difference, and you get the same result, right? That you can predict the absorption of benzene, absorption spectrum of benzene fairly accurately by assuming that benzene looks like a circle. Right, so this theory is really quite powerful. Even though we've simplified it quite a bit, the point of the fact of the matter is that electrons aren't really doing anything particularly interesting or exotic on the grand scheme of things in molecules. They're just acting like they're trapped inside of a box, and so their energy levels tend to be spaced like you would expect for a box. Of course, there are exceptions. Right? Obviously, in this case, this is a very simple case, but we still have a percent error. The question is, where does that percent error come from? And that tends to be, that's actually a very difficult question to answer. Right? So in general, a particle in a box will get you 90 to 99% of the way there to the correct answer. And that 1% at the end is actually exponentially difficult to solve. And in fact, this was known for a very long time. Right? People solved the particle in the box in the 1920s, saw that it worked really well for these molecules, and then tried to figure out how to improve their guesses, right? How to make the theory more, what's the word I'm looking for? More sophisticated. And that is still an ongoing process. I will talk, when we get to molecules, we'll talk about the hydrogen molecule, the simplest molecule you could probably think of. And calculating the energy of the hydrogen molecule turns out to be something that is still being done today. There's still always improvements to be done, and they're still being published. Right, so what you'll find over and over again in quantum mechanics in this class is that we can solve very simple problems and get really good predictions that are 90 to 99% accurate. Getting an extra 10 or 1%, that last 10% is really, really tough. And it's the entire point of why there are computational chemists, because that's a tough thing to solve. It turns out that a lot of interesting chemistry happens in that 1%. Benzene's a really great example of that small difference between a circle and a hexagon makes a huge difference in its spectroscopy and its reactivity. Right? So it takes a long time to really understand those things, but in the end, these theories are pretty good, right? These simple theories get you pretty close to the correct answer. Okay, so I want to hold on to this butadiene example for the rest of the class. Because what I've done here is I've somewhat convinced you that spectroscopy is possible, right? That we can do spectroscopy on this molecule by shining UV light at it and excite an electron from one level to another, right? We would expect that that molecule absorbs that energy, right? And we would expect that there would be, in our absorption spectrum, that there would be an absorption corresponding to this transition between the n equals 2 and n equals 3 level. All right, so that's spectroscopy right there. We know that if we can make this electron go from here to here, then it's going to happen at this frequency or this wavelength. Now the question is what's the probability? Is it actually possible to move this electron from here to there? Okay, so we've calculated the frequency, but we haven't calculated the probability. Okay? And that's the important part about quantum mechanics, is that we can calculate energies, but we must also calculate probabilities. Right? We can calculate energy differences for anything we want. But as we'll find, some things aren't allowed. Some things are actually forbidden. And the question I want to ask today is exactly that. Is it actually quantum mechanically allowed to take this electron and put it in this state? Because it might be forbidden. There might be a probability of 0. We don't know. And so I want to explore that today. By the end of this class, you'll be convinced that we can do spectroscopy. Right? We're literally deriving spectroscopy today. We'll come back to it, of course, and do it in more detail for real systems. But let's think about it for a particle in a box. All right, so the first question I want to ask is this. Let's prepare our system in some state. All right, so we have an electron in a box. All right, so let's say we have our electron, and our wave function is some wave function of the particle in a box, psi n. Right, so this is a particle in a box wave function, PITB wave function. All right, so maybe we have it in a ground state, n equals 1. Okay, so what's the probability of observing the system in another state, e.g. psi m of x, where m is not equal to m? Okay, so imagine that we know our electron is sitting here in the ground state. And the question is that when we do an observation of it and ask it, where are you? What's the probability of seeing it somewhere else? Like it's magically teleported, right? This might seem like a trivial question, but in fact, it's not always obvious, right? Is it always the case that the electron exists in the state that we prepare it in? So let's calculate that. So the probability remember that probability is proportional to psi squared. So what's the probability of preparing the system? So the initial wave function is psi n of x, and the final is some new wave function psi m of x, n not equal to m. Right? And so the probability of finding the system in a new state is going to be proportional to the product of the two wave functions. Okay, so to calculate this difference in problems, the probability of finding the particle somewhere else other than where we started is going to be proportional to proportional to the product of those two wave functions, right? Which means that the total probability, we'll call it of the n state going to the m state, call that a transition, is equal to the integral from 0 to L of psi m of x, the final state, times the initial state. Final times initial. Okay, so let's calculate this. Let's just pick, for instance, let's just pick n. Let's just pick two numbers. Why don't we just pick two numbers and just see if it works? All right, we don't have to prove it for any n and m. We can, but let's just for shits and giggles, let's let n equals 1 and n equals 2. All right, just do the simplest possible case. So we have the wave functions for, right, we know the wave functions for the particle in a box, so this is equal to integral from 0 to over L. The wave function for the m state is square root of 2 over L times sine m pi over Lx. And we multiply that by the same function, but with n instead of m. Dx. All right, so I'm going to do a little bit of math here, simplify things. This ends up being 2 over L, integral from over the whole box, 0 to L, of sine m pi over Lx, sine n pi over Lx dx. Okay, so we have a product of two functions, and because n and m are not different, these are two different frequencies, if you will. So we have two sines moving at different frequencies. So let's let n equals 1 and m equals 2, and I'm not even going to do the calculus. Instead, let's just graph it. All right, let's graph these two wave functions and multiply them together and see if we can come up with what if the integral is 0 or not 0. So let me draw it this way instead. So let me draw a line. This is our box, if you will, between 0 and L. We have two colors for each of our wave functions. So we'll let this be m equals 2 in green and n equals 1 in red. So I'll draw the n equals 1, 1. It looks just like this. There's n equals 1. Now what does n equals 2 look like? It's going to go down like that. Okay, here's the whole way. Okay, so now this is n equals 2. So now let's multiply them. All right, so now we're going to do m equals 2 times n equals 1. All right, what do we get? Well, notice that the n equals 1 is symmetric about the middle of the box. Actually, both of them are. But the important thing is that the sign changes. The sign changes for the m equals 2. So the product of this actually looks like is an odd function. Changes signs right at the center. I'll just write the product like this. Right, that's the product. These are equivalent. Same size, right? So the integral of this is 0. Integral of this function, the product of these two is 0, right? They cancel out, right? You have the two symmetric functions, one's even, one's odd. Symmetric about the center. So your result is now odd or anti-symmetric, right? Changes signs about the center. So, and each side is equal and opposite to each other in area, but naturally it sums to 0. So that means that there is no probability and in fact, this is true for all m not equals to m. Okay, it doesn't matter which number we pick. N equals 1, m equals 3, 4, whatever you want. It doesn't matter. It's not too hard to prove, and you can show that it's always equal to 0 when they're not equal, when these indices are equal, and that it equals 1 only when m is equal to n. So let me just write it like that. Okay, so the only state you'll ever find prepare your particle in some state, the only state you're ever going to find it in is the state that you put it in. All right, that's really powerful for us because now there's no confusion, right? If this were not true, if it were possible for us to prepare an atom or an electron in one state and then observe it in a different one, then all hell breaks loose, right? Imagine how chaotic that would be. Then you would have to know the probability of every state, the transition to every state. And that would be really difficult, especially for complicated systems. But here we're guaranteed that for a particle in a box, that the only states that the only transition you can get is no transition, right? That once you prepare a state prepare the system in a specific state, it always stays in there for all time. We'll always observe it in the same state. Right? That's good. That at the very least knows that our system is stable. And this allows us to introduce our next postulate. This turns out to be general. I don't know what number this is. 4, 5, 5. We call it orthonormality. All right, and let me define this explicitly. Assume that a system is represented by a set of wave functions psi n of x, such that when we apply an operator to it, to psi n of x, we get some number a sub n, psi n of x. And then if we apply the same operator to a different function, psi m of x, we get a different number. Where, I'll write this in different color, where a sub n is not the same as a sub m. Right? That basically means if a, the operator, is the Hamiltonian energy, then these states have different energies, and that the indices are different. Okay? So we're confirming here is that we have a set of states that satisfy the Schrodinger equation, and we have two states of different energy, effectively. That's all this is saying. It's not a very good color. Okay, and therefore, this guarantees two things. One, if this is true, then, let me write this in, then the set of functions, psi, this is the set of wave functions, is called orthogonal, which means that if you integrate over all space, right, we do the probability of these two different wave functions together, then you only get two results. Either 0 if they're different, or 1 if they're the same. Okay? So the cool thing is that when we solve the Schrodinger equation and get a set of wave functions, this is implicitly or explicitly encoded into them. The entire point of solving the Schrodinger equation is to generate a set of functions that are orthogonal. That basically every state is individual and isolated from each other. Right? There's no communication between the individual states. That they're well-defined states of well-defined energy, and that once you prepare a system in that state, it never leaves. Right? So therefore, it's always going to be 0 if the states are different, and 1 if they are the same. We use a symbol for this. There's some notation here I want to use. I don't know if it'll come up a lot. We call it the Kronecker delta function, which is delta mn, which returns two values. 0 if m is not equal to n, and 1 if m equals n. All right, this is the Kronecker delta function, and it just basically is just a way for us to encode this behavior into a single variable. All right, so example, Kronecker 1,1 is 1, Kronecker 1,2 is 0, and so on and so forth. Right? So it's just a label, if you will. So we call this Kronecker n. Okay, it's just a notation. There's actually interesting mathematics with the structure system. We can use it to define states that are defined in position or momentum, but we won't do that here. So this actually has some structure to it, but it's not relevant at the moment. Okay, and so this means that they're called orthogonal. So when you solve the Schrodinger equation and generate a set of wave functions, those functions are explicitly orthogonal, which means that this property is the case. One more comment. Wave functions that are orthogonal and satisfy that when you square a wave function by itself and square, you get one back, right? That's the idea of normalization. All right, we call this normalization. That we call the set of wave functions orthonormal, right? So we portmanteau the word orthogonal and normalize together to form orthonormal. So in general, solutions to the Schrödinger equation always lead to a set of orthonormal functions. If you come up with a set of wave functions, imagine that you can't solve the Schrödinger equation, you just want to guess the wave functions. Right, you just come up with a function, you just guess. And you come up with this set of wave functions and you calculate the orthogonality. And if you don't get this response, 0 or 1, if you get something in between, right, or if they're not the same, they get something that's not 0, then they can't be solutions of your problem. Okay, so every solvable physical system, I'll write it this way, every physical system, physically realistic, we'll call it, can be represented by a system of orthonormal wave functions. You're always guaranteed to be able to find one, that they exist. You might not be able to find them, but you know that they exist. Finding them is a different question, but you know that they exist. So anytime you ever see, if you put a molecule or something in, you see a spectrum of lines, right, where you absorb different energy levels, energy level transitions, and you see absorption. That is a product or a consequence of orthogonality. Right? The only way to represent a spectrum is to define the states that each of those transitions in your spectrum represent, transitions between, into orthogonal functions, right? Every physical state is an orthogonal function. Right? And that has to be satisfied. We didn't worry about it with the particle in the box, because when we did the particle in the box solution, it just came out of the math. Right? I just showed you that. We just plugged in n equals 1 and n equals 2 and showed that they integrate to 0 when you do the product and integrate it. Right? So it's already built into the math. But we're going to come up to it. We're going to come into situations in the future where we might want to guess the wave function or come up with a formalism for the wave function to represent a system, and it's not necessarily going to be orthogonal. And so we're going to have to figure out how to make it orthogonal. And in fact, there's always a process to do that. You're always guaranteed that if you come up with a set of functions to represent your system, that you can make them orthogonal. Right? We'll see that in molecules especially. Molecules will be super important. This will be a super important fact, that when we represent molecules, when we want to calculate the wave functions of their bonds, we're going to want to represent molecules as sums of atoms. Right? And the atoms have their own orthogonal wave functions in them. But when you add them together, like your butadiene, you add the carbon wave functions together to form butadiene, that combination isn't orthogonal. And so there's actually a transformation we can do to make them orthogonal, to have an orthogonal representation that now represents the actual physical system. All right, we'll see that play out time and time again in this class. It's kind of abstract at the moment, but it's essential for us when we want to represent a physical system. All right, that we have to come up with a set of orthogonal functions. All right, and we're going to come up with strategies to do that. Okay. So now what we know is, well, this is a problem for us in spectroscopy, right? Because in spectroscopy, we want to take a state, say where our system starts at n equals 1, and we want to move it to n equals 2. right? And by doing this calculation, we realize that that's not possible by the system itself, right? If the system just exists by itself, we start at n equals 1 and we want to move to m equals 2 in this case, the probability is 0, right? So what this tells us is that for just the system alone, you can't have spectroscopy. Right? Something else needs to occur. Right? The system by itself can't magically move in between states. So there has to be something that induces a change in the state. Right? And that's where I want to get to the final postulate today. I'm just going to jump right into it, and then we're going to apply it. Which is called completeness. This is probably the most powerful postulate in all of quantum mechanics, but it's not really. They're all powerful, but this one's kind of hard to see. And I want to use spectroscopy as an example to motivate our discussion. Let the set of wave functions psi of n of x be a set of orthonormal wave functions that satisfy the following property. The Schrodinger equation. Right? So let's have a system. We've calculated a set of orthonormal wave functions that satisfy the Schrodinger equation, right? That they're the states of our physical states of our system. Then define a new wave function we'll call it big psi. I'll put some horizontal lines to indicate that it's a capital psi, where psi, big psi, is a sum of smaller wave functions. Okay? So I'm going to, smaller wave functions of our system, where the coefficients, where Cn is a coefficient, a number, such that the sum of all the coefficients squared equals 1. Right, the idea is that we're distributing the state into multiple states, so the total probability of the system has to be 1, so the weights of each of the states has to be 1. Okay? This also satisfies the Schrodinger equation. Okay, so what we can do is we come up with a set of orthonormal functions that satisfy our system. Then we can create a new wave function that's a linear combination of the original wave functions, and that also satisfies the Schrodinger equation. Okay, so our system can be not only in just one state, but it can be in many states at once. We call this expansion a superposition of states. All right? You've heard of this before if you think about Schrodinger's cat. Schrodinger's cat, the idea is that Schrodinger's cat has two orthonormal wave functions, dead and alive. It's got an on-off switch. Right? There's only two states in its system. Right, we can do some observation to tell if it's, we can apply a Hamiltonian or some operator to observe whether it's alive or dead. Right, this is our EC, or what do you call it, like an EKG operator on our cat. And it turns whether it's 1 or 0, alive or dead. Okay? And so we have two wave functions that our system is, our cat is represented by, the alive wave function and the dead wave function. So let me write that down. So Schrodinger's cat. Let the D operator be the living operator, such that d psi is equal to 0 times psi if the cat is dead, and d psi equals 1 times psi if cat is alive. Okay, where psi is, or our cat is psi. Okay, we have a wave function with psi. All right, because our cat is a quantum mechanical system, so our big cat is actually a representation, our big cat wave function, our wave function for our cat is actually a sum of our alive cat wave function plus our dead wave function. All right, so the cat can be in either two states, alive or dead. And so the real cat, the cat's actually a sum of the two. And of course, C alive squared plus C dead squared is equal to 1. Right? It has to be either or, so they have to sum the 1. Okay, so our cat is, so before observation, our cat is actually a superposition of the two. All right, so we put our cat in the box. Our cat can either be alive and dead, which means that its wave function has to be a sum of the two wave functions. Right? It has to be a superposition of being alive or dead. And then we do our observation. We measure the living state of the cat. Okay, so we apply D. This is our box. This is our experimental box. We apply it to our cat. Let me draw a crappy cat here. Put X's there just in case maybe it's alive or dead, I'm not sure. Right? And what do we get out? We either get out a 0 or 1, alive or dead. And here's the question, what is the wave function after the measurement? Well, if the cat's dead, then the wave function of our cat is psi dead. And if it's alive, it's psi alive. So this is the entire point of Schrodinger's discussion, is that the cat is both before observation, when you put the cat in the box and you leave it there, the only way the math works out is that if you represent the cat as a sum of being alive and dead simultaneously. You don't actually know what the chance of it being alive is or the chance of it being dead is. It could be 50-50. Could be 50-50. But you only will know when you measure it, right? When we apply the operator to the wave function, it's either going to return 0 or 1. Let me show you that. Right, so let's apply the wave function to the cat. This is going to be the wave function applied to, we'll call it CA psi A plus CB psi B. All right, that's all. I'm sorry, BD, sorry. C, that's for dead and alive. Right? And because it's linear, this is CAD psi A plus CD D hat psi D. And so what do we get? Well, if it's alive, we get psi A, and we get a 0 here. Right? But if it's dead, this is if CD is equal to 0, right? There's no chance of it being alive or dead. But we also get CD psi D plus 0 if the chance of it being alive is 0. Okay? All right, so those are the easiest answers. But notice that there's also a possibility where the chance of either one is not equal to 0. Right? So we have two simple solutions, either alive or dead. It's going to either give us back the original wave function to the dead wave function. But notice that CA and CD can be any number we want, as long as they sum to 1. So what happens when we apply D to this wave function? So let's say there's a 50-50 chance. Okay, so that means that CA plus CB squared equals 1, and CA is equal to CB squared. Right, the probability of, this is D, sorry, not B. Right, they sum to 1 and they're equal to each other. And that turns out that once you do the math, it's not too hard to do that. That CA is equal to CD, which is the square root of 2 over 2. Right, so the wave function of our cat being half dead or half alive is the square root of 2 over 2, which I'll write as 1 over the square root of 2. It's the same thing. Psi alive plus psi dead. Let me change this a little bit so that we don't get 0 back to make it simpler. So what are we going to call this? We'll call it A. It returns A or D. How about that? Alive or dead? They're just variables. Maybe you turn an LED on, right? If the cat's alive, you get a red LED, or a blue LED. If the cat's dead, you get a red LED. That's what D is. So now let's do the same thing as we did before. Let's apply our living operator, our EKG, to our cat. So that's going to be 1 over the square root of 2 times the operator D times psi A plus D psi D. Okay. And that's going to be 1 over the square root of 2. D psi A is going to be A, and D psi D is D. Psi A, psi D. Okay. And so that means then that what this means is that every time you measure the system, it's either going to come back dead 50% of the time, or so CA squared is 1/2 A, is 1/2, and CB squared is 1/2 as well. So what you get is when you measure the cat's aliveness or deadness, only 50% of the time you're going to find out the correct answer. Right? And this is what you want, right? You want it to come back that 50% of the time, the cat's 50% chance of alive or dead, that this comes back either 50% A or 50% D. Do 100 measurements of it, you should get 50 A's and 50 D's. So that means that the probabilities are 1/2. And so the only way for this math to work, right, to get the answer that we want, the probabilities and the statistics that we expect for a cat being 50-50 alive or dead, is if the cat is represented as a simultaneous superposition of alive and dead. Imagine now if we didn't add them together, maybe we had to multiply them together, or maybe you can't do this at all, you would never get this result back. Right? So the only way to get the probability of equal weight between alive and dead at the 50-50 chance is that if the cat starts in a position that's both alive and dead simultaneously. Right? So this is kind of a very weird situation. This is very counterintuitive, because if the cat were a physical classical object, just a normal cat, then it's always either going to be alive or dead, regardless of whether you observe it or not. But in quantum mechanics, the only way to get the right numbers out, to predict the correct probability of, say, if your cat's 50-50 chance, is that the cat has to start in a position that is both simultaneously alive and dead. Right? So in general, systems are represented not by a single wave function, but by an infinite sum of its wave functions. Okay, so for a particle in a box, the wave function, the actual wave function that represents our system when we create the particle in the box, is an infinite sum from n equals 1 to infinity of some coefficient c sub n times that wave function, particle in the box wave function. All right, so in fact, if you put an electron in a system in your box and you just leave it alone, you can't observe it, the system's not actually just in one state all the time. It's actually in a superposition of all the states. It can be in any of them. It's not until you ask it a question. It's not until you ask psi a question. And let me ask a very simple question. What's your energy? that the system returns a specific value. Okay, so the idea is that any quantum mechanical system, when it's created, right, the moment that it's created, that the system is actually represented, the only way that the math works out is that it's in the state that is a superposition of all of its states. And it's not until you ask it a question that you get back an answer. Right? If we prepare our electron in our box and we don't observe it, we just put it in there and leave it alone, there's going to be some probability based on whether it's going to return the first excited state or the ground state. Right? There's a different probability of it being in a specific state. But before you do that observation, it's on all of those states simultaneously, which is very counterintuitive. We're going to see this time and time again in this class, this idea of superposition. And it's going to help us do spectroscopy. How much time do I got left? Just enough. Let me explain why that is. So how do we do spectroscopy? We have two states, let's say psi m and psi n equals m, where the difference in energy between them we'll call h bar omega, right? Some energy. Okay, and now, but we know the question is if the system has energy h bar h omega, what is the probability of transitioning from n to m, right? What's the question of it? What's the probability of taking, if you put enough energy into the system, what's the probability of it going from n to m, right? Probability of taking the state from one system and putting it in another one. And of course, unfortunately, the integral of psi m psi n dx is equal to 0, no probability, right? So the system by itself can't do it. Right, so the system doesn't spontaneously go from one state to another. Right, so that's a problem, but maybe if we introduce a perturber, something new to the system, maybe we can change that. But remember, spectroscopy is the study of matter with light. Right, there's something we haven't considered here yet, the light. Right, this transition is impossible because nothing's happening, right? There's no light here. We're just asking what's the probability of taking one state and putting it in the other. There's no probability. But what happens if we shine a light at it? So let's take let's define some incident light. Okay, so here's our particle in a box. Here's our electron in n equals n state. Here's n equals m. We have an electron here. It has a difference in energy of h omega. And let's shine light at h omega. So the frequency of this light is h omega from our light bulb. All right, so let's shine light that's resonant with that energy difference. Well, now what we're doing is now the system is not just two states, but there's also a wave in there as well, right? We have waves associated with the wave functions of those states, and they're interacting with a light wave. So now let's define the electric field of the light as an operator. It's our probing tool, right? So it's just, you can represent it as an operator, right? This, remember, an operator is just a box that we ask questions with for asking questions about our state with light. Right? We'll call that, I don't know what we want to call it, we'll call it E. And it's equal to it's proportionally equal to e to the I h omega times x, which is equal to the cosine, it's actually 2 pi, sorry, let me change that. I gotta get the units right. That's 2 pi I h omega times x. That's a complex wave, but we can represent it as a cosine plus a sine function, right, where our frequency is 2 pi h omega. Okay? And what we can assume that h omega times x is much greater than h omega. X is large. Right? Basically, the wave is propagating over a larger space than the box. This means that delta x is much greater than L. Right? The wave is propagating forever and the box is defined. Then we can write E, the operator, as it turns out the math works out, cancels out beautifully, and you're left with a position operator times E, where this is the charge of the electron. Right? The reason why this works is that we represent e to the x as 1 plus x squared over 2 plus x cubed over 6 plus. This is the Taylor expansion. And we can neglect these terms because they're small. And so we're left with 1 plus x. And the operator 1 doesn't give us anything, so we're just left with x. Just x left.
Professor,
yes?
Since there is an I in front of the sine, should there also be an I in front of the cosine, or no?
No.
No?
No, so this is actually, maybe this is, I always assume that this is known by everybody. This is called Euler's formula. I'll just write it here. It's a good one to remember. I learned this in Algebra 2. I'm not sure everyone does. If you take e to the ix, this is cosine x plus I sine x. By definition.
Okay.
Yeah. So that's why I'm using that. But anyway, so once you do all this math, there's a lot of math here to simplify. But anyway, what happens is that the electric field can be just treated as x. All right, so the electric field operator is just a displacement operator, because the displacement of the wave is roughly proportional to the displacement, which is x. Okay, so that means then the probability of n to m with light is going to be equal to the average, is going to be equal to minus e times the average value of the x operator between the two states. So that's minus e integral from 0 to L of sine m pi x over L times x times sine n pi x over L dx. Right, so what we're doing now is we're just calculating a probability distribution, but we're adding this magic operator that represents our electric field. This is what's called the dipole operator. We'll talk more about dipoles when we get to molecules. But anyway, the probability of when you shine light resonant two states, the probability of it going from one state to the other is proportional to this integral. Right? Now the question is this equal to 0 or not? And it turns out that's kind of a tricky, this is kind of a tricky integral to evaluate. But I have the solution here. Let me simplify this a little bit. I missed a factor of 2 over L on the outside, right, at the normalization constant. So this is minus 2e over L integral x sine m pi x over L sine n pi x over L dx from 0 to L. And so that's the probability of transitioning from one state to another with the presence of resonant light. And it turns out that the integral of x sine So I'm just going to write down the standard solution for this. I looked it up on Wikipedia. Actually, I did Wolfram alpha. Is equal to is 1/2. Now I'm going to define two variables here to make it easy. Delta is equal to A minus B. Those are the coefficients. And the sum is equal to A plus B, just to make things simpler. Is equal to x sine delta x over delta minus x sine sigma x over sigma plus cosine delta x over delta squared minus cosine sigma x over sigma squared. Okay, so we got this big long integral. And so let's define delta and sigma in terms of our problem. So delta is going to be the difference of the two frequencies here. So that's going to be m minus n pi over L. And sum is m plus m pi over L. Okay, so we have this big long integral to calculate. So this integral simplifies to minus e2 over L times 1/2, so that the 2's cancel out. And then we're left with this long integral here that we need to evaluate. So x sine, so let's factor out the pi over L, because we have a pi over L here and a pi o squared over L squared here. Let's do that. Let me simplify this a little bit. So this is going to be e over L, and then we have pi over L x sine delta x, which is m minus n, pi x over L over m minus n, minus x sine m plus n pi x over L divided by m plus n, and then we have a square term here, so we have a slightly different term. Again, this integral is long, but what we're going to find is the answer is pretty straightforward. We have a plus and a minus here, so let's do plus pi squared over L squared. And this is going to be equal to cosine m plus n pi over Lx over m plus n squared minus, so this is minus, sorry, the difference, minus the sum of the sums, minus the sum frequency, x over m plus n squared. Okay, so this is a big equation, and we need to evaluate this from 0 to L. All right, so let's do it for 0. 0 is pretty easy. Look, if we put x equals 0, these terms go away. So for x equals 0, we have minus e over L. This whole term is 0 plus, let's think about this, cosine of 0 is 1, right? Cosine of 0 is 1, so these are 1. So we're left with pi squared over L squared, 1 over m minus n squared minus 1 over m plus n squared. All right, so that's our upper bound, our lower bound, and then for L, minus e over L. Let's look at this first term. Well, if x is L, then it's m minus n pi. And so that means that this is, depending on the values of m or n, then it's either at 0 or 180 degrees, which means it's 0. So these are 0, because the sign of any integer pi is 0. And then we're left with some cosine terms. So the cosine of m minus n pi over Lx, the L's cancel at x equals L, so we're left with m minus n pi, so some integer multiple of pi. And of course, depending on what if it's integer, then it's always going to be 1 or minus 1. Right? So it's going to be either plus or minus pi squared over L squared cosine. So what cosine is either 1 over m minus n squared plus minus 1 over m plus n squared. All right, so if m minus n is equal to an odd number, let me think about this for a second. If m minus n is equal to an odd number, then it's minus, this is minus 1, and this is positive 1. So this is positive if m minus n is odd, and negative if m plus n is odd. Oh, sorry, if m minus n is odd. That's it. Yeah. This one doesn't change. It's always. Yeah. Okay, so and negative if even. Okay, so now we just take the difference of these two, and notice that so once you do this math, you're going to have, if you notice, these look very similar to each other, right? In fact, they look identical to each other, except when this side is different, right? So when we take x, we take the solution of x equals L minus x minus 0 equals 0, right? If we take this minus this, then if these are both positive, then the whole thing is 0. So if, actually, so I have this flipped. I apologize. I just realized this is even and odd. I messed up my math. Sorry. So if they're even, it's plus. So if m minus n is even, probability is 0. If m plus n, if n minus n is odd, so for instance, 1, if they're different by 1, right? You get 2 times this formula. The probability is not equal to 0. Okay, so basically it says that if your quantum number or your state jumps by +1, +3, +5, and so on, then a transition is allowed. All right, so what does that tell us? Well, remember, we initially remember that our light was resonant with an n equals 1 transition, right? It goes from the 0 to the 1 state. So let me just write that down. So let's go back to our particle in the box. So here's our n equals 1 state. Here's our n equals 2 state. Okay, like that. And we shine light at it such that the frequency is resonant. The frequency of the light is resonant with the energy difference of that system, or the wavelength is resonant with the energy difference of the system. Then m minus n is 1. Therefore, the probability, which is the integral of psi m x psi n dx, is not equal to 0, which means the light excites the electron. Right? We've just done spectroscopy. Right? All spectroscopy is, right? And so what this tells us, though, is interesting. If we, for instance, want to shine light now that's resonant with two jumps. Right, imagine now we measure this difference, and we shine light at that difference. Nothing happens, right? Because 3 minus 1 is 2, and if the difference is even, then the probability of that transition is 0. Right? So for the particle in the box, transitions where delta n is equal to 2k plus 1, odd, are allowed, and with equals 2k, even, are forbidden. All right, so what that means is that if we expect to see a spectrum of absorption lines associated with the connectivity of our states, we're going to see a sequence of, say, n1 to n equals 2, n2 to n equals 3, n3 to n equals 4, and so on. but we're never going to see n equals 1 to n equals 3, or n equals 2 to n equals 4, but we will see n equals 1 to n equals 4, right? Because that's delta n equals 3. Right, so what we would expect, how much time do I got left? I'm out of time. Okay. Yeah, so what we would expect just really quickly is if we were to take a spectrum and we plot frequency versus intensity, we first get the n equals 1 to n equals 0. That's going to be at, or sorry, n equals 2 to n equals 1. There's no n equals 0 state, sorry. That's going to be at 5 h squared over 8 ml squared. We're going to see a line there. And then at 9 h squared, 8 ml squared, we'll see the n equals 3 to the n equals 2. Right? But then when we go to the, say, the n equals 3 to the n equals 1 state, which is going to be at 9 minus 1, which is 8 h squared, oh, it's over here actually, n equals 3 to n equals 1, which is 9 minus 1, that's 8, h squared, 8 ml squared. There's nothing there. We see no line. All right, we're going to see a pattern of lines corresponding to delta n equals 1, but we're never going to see no lines corresponding to delta n equals 2, right? Which will be in the middle. Right? They don't appear. Right? So spectroscopy has two different components. One is frequency, right? Spectroscopy is just determining where energy level spacings are. That's where we see absorption. It's where the system can absorb that light energy. But there's also the y-axis, the intensity. And the intensities of lines, intensities of spectroscopic transitions, or lines, is purely determined by probability. Right? The more probable it is to transfer one system to another state, the more intense the absorption lines are. If there's no probability, if it's forbidden by math, then you'll never see a line. Right? We'll come back to this in spectroscopy at the end of the class. All right, so that kind of leaves us now with all of the postulates. We have one left, which is, we've done everything without time. Now we have to include time, right? Maybe we want to watch our system evolve in time. And so the last postulate will be time dependence. We'll talk about that. It's a very interesting topic. We'll talk about what spectroscopy means in the time-dependent view, right? What is happening to a system when it absorbs energy. And that'll give us enough tools to do the rest of the class. Anyway, have a lovely day. Have a good one.
Going, Dr. Seibert.
Yeah, you too. Thank you.